All right, so now we understand how we create our interval. We start with our point estimate, we add or subtract a margin of error. We need to know how the heck we calculate that margin of error. So the margin of error is comprised of two pieces. First, it has this idea of a confidence level. Confidence levels are usually set in advance, and the very common ones are 90%, 95%, 99%. These basically get us to that Desmos activity that you guys ran through. It's about this idea of like, we know that we kind of have this thing that we call a standard error. We're going to get that on the next page. It's our standard deviation guess, right? We don't know exactly what our standard deviation is because we don't have P. So we use P hat, Q hat, all over N as our standard error. This gives us basically the bunny hops. And this is what that Mr. Nystrom video has on it that's really good. If you haven't seen that, if I put this up for a class in the future, scroll down. It's going to be below. But the idea here is we're going to say, okay, I don't know exactly where P is, but I have a P hat. I'm going to start there. And I'm going to jump out based on standard deviations that I don't have. So we use these standard errors. The confidence level essentially gives us how many bunny hops, how many of those standard errors we want to jump away from our P. In the activity, the confidence interval intro activity, I had you guys jump away one standard deviation. I'll just go ahead and throw a little normal curve on top of this. I had you guys go out one standard error. And then we know that about 68% of the data is within one standard deviation of the mean. So using that sort of backwards, we had about a 68%, don't want to say chance, but there was about a 68% chance that you guys caught real P when you made your intervals. And then if you go out two standard deviations, which I had you do next, which should have been wider, now you're looking at 95% of the data, roughly, right? I'm using the empirical rule estimates here instead of the exact values. But that's what these pieces are all about. In fact, if you find this Z star, which that's what these confidence levels give us for 95%, that's exactly how many bunny hops, how many standard errors you want to go away from your estimate. And your Z star for a 95% confidence level is 1.96, right around 2. Obviously, they go out just a little bit further to get that exact 95%, which we don't have with the empirical rule. So that's one way we're going to use these confidence levels. We'll get more practice with that, and I'll talk a little bit more about it, especially because I have questions on both the practice quiz and the knowledge check about finding a critical value for an odd confidence level. But I want us to understand what the heck this confidence level is telling us. So we're going to move on and look at exercise 3. So exercise 3 is another one I really like doing with a class so we can have some back and forth. So I'm just going to try to run through it, but you're welcome to pause and try these things on your own. So if you guessed at the true proportion of students at Mesa who are Hispanic, I usually will just sort of throw it out to the class, and I get guesses anywhere from like 25 to 60%. So let's say, I don't know, throw down whatever number you want. You don't have to use mine. I'm going to go with 40%. So you can, of course, put 40% instead of 0.4. So that's my guess as to real P. Now, of course, it's just a guess if there's no real data involved here, but I want us to get this feeling of what a confidence level gives us. So if we were going to guess at this interval and say, okay, well, how confident am I, plus or minus, that you are 80% confident catches the real proportion of Hispanic students at our school, you might say, well, let's go from 30 to 50%. I'm pretty sure it's less than half. But more than, that seems, I feel pretty good about it, right? And of course, your interval might be different than mine. But on the second one, this is where I'm hoping we get that bit of an aha moment, because it's a question I love to ask on the exams and you see on the knowledge check. Create a confidence interval that you are now 99%, this interval that you are now 99% confident would contain the actual proportion. So if you're thinking about this, hopefully, I always get some snarky student when I do this in school, and I appreciate snark, who says, well, I'm just going to shade the whole freaking thing. Like, I am 99% confident that the value is somewhere in there. Totally legit. Totally legit. Because the takeaway I want you guys to have from this is that if I want to be more confident, I need to make a wider interval. And there's nothing saying we have to keep it symmetric here, but because that is how these intervals are created, I'm going to do it. But this is the idea. 99% is going to be larger or wider, I guess I should use instead of larger. And that's because it's a P catcher, right? It's a parameter catcher. And if I have a bigger net, it's more likely that I've caught the real value. All right, bigger net, more likely that it contains the real value. Now, here's the thing. There's a trade-off, right? Having a wide interval is kind of crappy. If I say that, well, there's between 10% and 70% Hispanics at Mesa, that's a pretty useless statement versus between 30 and 50%. So there's always a trade-off in terms of our accuracy and our confidence. So these two things are tugging at each other when we do a confidence interval. And that's something I want students to take away, because they tend to get these two ideas conflated, right? More accuracy, more precision seems great, and it is great, but we have to sacrifice some confidence to do that, or vice versa. So the real value, if you wanted to know, I think last I checked was 35%. So both of these intervals catch the real value. Obviously, I knew what I was doing. I knew what the answer was. But again, there's that trade-off of precision versus confidence.